Welcome to the lecture on residuals and residual variation. My name is Brian Caffo, and I'm the instructor for the regression class as part of the Data Science Coursera specialization. Let's start by talking about our motivating example using the diamond data set. Remember, in this data set, the diamonds were diamond prices in Singapore dollars, and the explanatory variable is the weight of the diamond in carats. We'd like to talk about how we can explain variation in diamond prices using their mass. Let me generate a plot. Last time I went through the commands for generating the plot, so I won't do this again, but here's my ggplot, and let me zoom out. So what we're interested now is explaining price on the vertical axis by mass on the horizontal axis. If we had disregarded mass, we would have all these points. We would look at their sort of projection onto the vertical axis, and there would be a lot of variation. If you were to disregard mass, there would be a lot of variation. When we consider mass, there's much less variation, because now we're talking about this variation around the regression line. The variation around the regression line is residual variation, that variation that was left unexplained by having accounted for mass. So we start out with a lot of variation. We've explained a substantial fraction of it by the linear relationship with mass, but there's some leftover variation. We'll call that residual variation. These distances that make up the residual variation are called the residuals, and that's the topic of today's lecture. The residuals are quite useful for diagnosing many things, including poor model fit. Let's remind ourselves of the model that we're considering. Our outcome in our example, which would be price, is yi, which we're assuming is a line, beta naught plus beta 1 xi, where xi in this case is mass in our example. We're adding on some Gaussian error, epsilon I, which we're assuming to be normally distributed with a mean of 0 and a variance of sigma squared. We haven't explicitly used this normal assumption yet, and that'll be coming later on in some subsequent lectures. Remember, the outcome is yi for predictor value xi at that specific index I. So yi is a price, xi is a mass. The point on the line corresponding to xi is yi hat. We can figure out yi hat by just plugging in beta naught hat plus beta 1 hat times xi. Well, our residual is nothing other than the vertical distance between the observed data point, observed outcome, yi, and the fitted value, yi hat. So ei is equal to yi minus yi hat. Remember, our least squares criteria tried to minimize the sum of the squared vertical distances, so in essence it was minimizing the sum of the squared residuals, summation ei squared. One way to think about the residuals are as an estimate of epsilon I, though you have to be careful with that, because, as we'll see later on, we can decrease the residuals just by adding irrelevant regressors into the equation. Let's talk about some aspects of residuals that will help us interpret them. First of all, their population expected value is 0. But also, their sum, their empirical sum, hence the empirical mean also, is 0 if you include an intercept. If you don't include an intercept, this property doesn't have to hold. Well, the generalization of this property is if you include any regression term in linear regression and our generalization in linear models, the sum of the residuals times that regression variable has to be 0. Residuals are very useful for diagnosing poor model fit, and we can create plots that sort of highlight and zone in on the aspects of poor model fit. Another very common use of residuals is to think of them as the outcome y with the linear influence of the predictor x having been removed. So for example, if we wanted to, in some subsequent model or some subsequent analysis, analyze diamond prices, but in a way that has already been adjusted for their weight, so calibrating all the diamond prices to sort of be on the same scale regardless of their weight, we would take those residuals from the model fit that has diamond prices as the outcome and weight as the predictor. So it's very common to take residuals and carry them forward in a later analysis where you want to think of them as the new outcome having removed the predictor at that point. But of course, remember, if you do linear regression, you're only removing the linear component of the predictor. So one should differentiate between residual variation, which is variation that is left over after the explanatory variable has been accounted for in a linear fashion, from systematic variation, which is variation is explained by the regression model. So again, residual plots can highlight poor model fit, and we're going to go through some residual plots here in just a couple of slides. Let's go through calculating residuals. We're going to use the diamond data set. Let's see, so our data is the diamond data set, so let's do that. I'm going to redefine price as y, x is caret, and n is the length of the number of pairs, just so I don't have to type so much. Now I'm going to assign to a variable named fit, I'm going to assign my linear regression object that gets created from LM. So let me do that. Now, the easiest way to get the residuals is just do resid of fit. So I'm going to define those as E. Let me show you another way to get the residuals that of course has to do the same thing. If I were to get my predicted fitted values, and remember, if I don't give the predict function new data, if I just give it the output from LM, the assignment from LM, then it will just predict at the observed x values. So y hat now is a vector of predictions at the observed caret values. Now, I just want to show you that my residuals calculated via the resid function are the same as the residuals that I'm calculating manually, which is just subtracting y and y hat. So the way to do that is just take the difference, the absolute differences, and find the largest one. And I see that the largest one is on the scale of 10 to the minus 13. So up to numerical precision, it's the same thing. Then lastly, I just want to show that if I manually even calculate the fitted values, coef fit 1 and then coef fit 2 times x, that I, of course, will get I get exactly the same number. So up to numeric precision, exactly the same. So the way you want to do it to get the residuals is resid, but hopefully showing you this other code will illustrate what's going on in the background with what the actual calculation that resid is doing. Finally, let me show you that the sum of my residuals is 0. Well, it's 10 to the minus 14th, which is close enough to 0 for me. And then also the sum of my residuals times the price variable, x. That also has to be 0. Well, 10 to the minus 15, so up to numerical precision is 0 in both cases. So the residuals are the signed lengths of the red lines that I'm going to show in the following plot. And I'm going to do this using base R graphics, just so I mix a little bit of base R with some ggplot graphics. So I'm going to create my plot here. There's my plot. I'm going to add the fitted line, and in base R, if you want to add the fitted line and you fit a regression line, you can just do AB line and put the object that you assign to the LM fit just as an argument, and it'll add the regression line. Here I want the line width to be 2, so it shows up a little bit better. And then I'm going to just for loop over the data values to add in the red lines. Let me zoom in and show you that plot. There's my plot. Now my residuals are these red lines, these distances, where if the point is above the line, the residual will be positive, and if the point is below the line, the residual will be negative. This scatter plot isn't particularly useful for assessing residual variation. Notice all of the blank space in this part of the graph, making the plot kind of useless for that purpose. So instead, why don't we plot the residuals on the vertical axis versus mass on the horizontal axis? Let's go ahead and run the code. And here's the plot. Now we can see the residual variation much more clearly. When you look at a residual plot, you're looking for any form of pattern. The residuals should be mostly patternless. Also remember that if we've included an intercept, the residuals have to sum to 0. So they have to lie above and below this horizontal line at 0. And you'd like them to be sort of nicely, in a random looking fashion, distributed both above and below 0. We can see some interesting patterns by honing in on the residual plot here. For example, we can see that there were lots of diamonds of exactly the same mass measured, and this sort of gets lost in the scatter plot. By zooming in this way, we notice that particular feature. Next, what we're going to go through is some pathological residual plots, just to highlight what residual plots can do for you. So I've concocted some examples that will help us to understand how residuals can highlight in on model fit. So let's look in the R Markdown file, and I'm going to show it again at the console rather than going through the slides so you can actually watch me doing this. X here is just going to be uniform from -3 to +3. So I've created a X variable that's just a kind of random smattering of points between the values 3 and -3. My Y is equal to X, so it's an identity line, but then I'm going to add another term that's sine X. So it should look like an identity line, but kind of oscillating around it a little bit. And then I'm adding some normal noise on top of it. So let me add my Y, and I'm going to switch back to ggplot because I like it better than base graphics now. So I've created my ggplot. I'm going to go ahead and add the smooth first because I want it as the bottommost layer, and then I'm going to add my 2 sets of points, and there's my scatter plot. And so let me zoom in, and it's a little difficult to see the nonlinearity. That sine X term is it's a little apparent, but it's kind of very hard to see. I think if I was looking at this, I would immediately notice something pattern-esque in the poor fit here, but nonetheless, it's maybe a little bit hard to see. Before I move on to the residual plot, let me make a comment. This model is actually actually not the correct model for this data, and this might happen in practice. This doesn't mean that this model is unimportant, right? There is a linear trend, and the model is accounting for it. It's just not accounting for the secondary variation in the sine term. So I just want to emphasize this in regression modeling, is just because you aren't fitting the actually correct model, that doesn't mean the model is itself useless. You have about, an average identity line here that represents the relationship between Y and X, and it explains a lot of the variation. So I just want to remind you that in regression, having the exact right model is not always the primary goal. You can get meaningful information about trends from incorrect models. So I just want to get that statement out of the way. But now let's hone in on the residuals. So plot the residuals versus X and see if it makes this component of the fit, the sine X term, more apparent. Okay, so let me plot the residuals versus the X variable. So just to describe what I have, I'm going to assign G as my ggplot. My X is, in this case, X. I've defined the X variable as the variable name X. But now my Y is not the Y variable, but it's going to be the residual from the linear model fit. And here I just grab it in that R command right there. Then my aesthetic for my ggplot just has X and Y as the names of the variables for the horizontal and vertical axis variables. So let me run that command, and then I want to put a horizontal line, reference line at 0, and then I want to add my points and set the axes how I'd like, and then let's see the plot. And there's the plot. Let me zoom in, and here is the plot, and I think what you can see is that this sine term is now extremely apparent. That what the residual plot has done is it's zoomed in on this part of the model inadequacy and really highlighted it, and that's one thing that residual plots are especially good at. I'm going to show you another one where, by all appearances, the plot falls perfectly on a line, but when you highlight in at the residuals, it looks quite different. So let me run the commands, and then I'll show you. So there's the plot. And then now, so look at that, and it seems like the points fall exactly on an identity line. Now let me highlight in on the residuals, and you see this trend toward greater variability as you head along the x variable. That property where the variability increases with the x variable is called heteroscedasticity. Heteroscedasticity is one of those things that residual plots are quite good at diagnosing. And you couldn't see it if I go back to this earlier plot. You can't see it at all here. Zoom in on the residuals, and there you see it there. Let me just zoom back here to how I generated the data just to illustrate it for you. My x variable is a bunch of uniform random variables. My y variable is my x variable, so an identity line. But then when I added the errors, the standard deviation of the errors, look right here, has the x term involved in it. And that's how I generated data with heteroscedasticity. So let's run the residual plot for the diamond data. So here I'm just going to add a column to the diamond data that is the residuals from a regression model fit where price is the outcome and caret is the predictor. So I run that, and now my data frame, has caret, price, and now the residuals. So I'm going to create my GG plot. My X label is going to be mass in carats. My Y label is going to be residual price. And I just want to emphasize that the residuals have the same units as the Ys. So the residual price is in Singapore dollars. I'm going to add my horizontal line. I'm going to add my points. And then there's the plot. So there doesn't appear to be a lot of pattern in the plot. So this is good. It seems like it's a pretty good fit. Let me illustrate something about variability in the diamond data set that'll help us set the stage for defining some new properties about our regression model fit. So I'm going to create now two residual vectors. The first residual vector is the one where I just fit an intercept. So the residuals are just the deviations around the average price. Then I'm going to find the residuals where I add in caret as a predictor variable. So now these residuals are variation around the regression line. So the first one is variation around the average price. The second is the variation around the regression line with carets as the explanatory variable and price as the outcome. So I'm going to run that. And then I want to create a factor variable that labels the set of residuals. The first one is just going to be labeled as a bunch of intercept only model residuals, and the second set are going to be labeled as a bunch of intercept and slope residuals. Then I want to create a GG plot with this data frame. My Y variable is going to be the residuals. My X variable is going to be the fit, which of the two fits it is, linear model or linear model with just an intercept, or the linear model with caret, the mass as the predictor. And I want to fill in my points based on with the color based on which fit it was. So I'm going to do that. And then the kind of plot I want is a dot plot. And then I want to put my axes labels the way I'd like. Now let's see the plot. There it is. So what we see on this left-hand plot with just the intercept is the variation in diamond prices around the average diamond price. So just basically the variation in diamond prices from the sample. What we're seeing in the rightmost plot, this is displaying the variation around the regression line. So what we've done is we've explained a lot of this variation with the relationship with mass. And what we're going to talk about next is R-squared, which basically says we can decompose this total variation, this variation in the Y's by themselves, maybe with just the mean, into the variation explained by the regression model and the variation that's left over after accounting for the regression model. So this is the variation that's left over after accounting for the regression model. So the sort of subtraction of these two would be the variation that was explained by the regression model. Well, there's a formula for that, and we're going to dive into that next. Let's talk about residual variation really quickly before we finish talking about R-squared. Residual variation is the variation around the regression line. So remember, our residuals are the vertical distances between the outcomes and the fitted regression line. Remember, if we include an intercept, the residuals have to sum to 0, which means their mean is 0. So if we want to take the variance of the residuals, it's just the average of the squares. So the sum of the squared residuals times 1 over n is an estimate of sigma squared, the variation around the regression line, the true population variation around the regression line. Now most people use n minus 2 instead of n, so it's not the average squared residual, it's kind of like the average squared residual. And for large n, the difference between 1 over n minus 2 and 1 over n is irrelevant, but for small n, it can make a difference. The way to think about that is, remember, if we include the intercept, the residuals have to sum to 0. So that puts a constraint. If you know n minus 1 of them, then you know the nth. Well, if you have a line term in there, if you have a covariate in there, then that puts a second constraint on the residuals, so you lose 2 degrees of freedom. If you put another regression variable in there, you have another constraint, you lose 3 degrees of freedom. So in essence, it's sort of like saying you really don't have n residuals. You have n minus 2 of them, because if you knew n minus 2 of them, you could figure out the last 2. And that's why it's 1 over n minus 2. So let me show you how you can grab the residual variation out of your LM fit and assign it to a variable. This way, if you need to work with it in an R program, you can actually grab the number, not just see it on the printout. So here I've defined my y and my x, and I've defined my fit as the regression model with y as the outcome and x as the predictor. Well, if you just do summary of fit and you don't do anything else, you just hit return, it'll print out the summary of the regression model, intercepts, slopes, estimated values, and so on, and you'll see the residual standard deviation estimate among the elements of the printout. However, if you want to grab it as an object that you can assign to something, just put $sigma. Then you can assign sigma to any other variable, so if you're using it in a program in some other way. This works out in this particular example to be $31.84. So here, let's just confirm that I'm not lying to you and that the formula works. So if I do resid fit, that grabs the residuals. If I square it, it squares them. If I sum it, it adds up the squared values. If I divide by n minus 2, it takes the average of the unique residuals. And then if I square root it, I get 31.84. So I wasn't lying. Now let's go back to this plot where we look at the total variability in diamond prices and then compare what happens to the variability when we explain some of that variability with the regression line. So the total variability is just the deviations of my data, the average squared deviation of my data around its mean, around the center. And just to make things easy, let's forget about the denominator and just talk about the sum of the squared deviations. Well, we might call the regression variability as the component of that variability that then gets explained away by the regression line. So we would take the points on the regression line, the heights, and that's the variability in the response that's simply explained by the regression line. And let's take how much that deviates around the average. So that's the regression variability. Then everything that's left over is that variation around the regression line, and that's the residual variability. And the interesting identity, and it kind of makes sense that this would be the case, is that this total variability, the variability in diamond prices disregarding everything except for where they're centered at, is equal to the regression variability, that is the variability explained by the model, plus the residual variability, the variability left over not explained by the model. because the residual variation and the regression model variation add up to the total variation, we can define a quantity that represents the percentage of the total variation that's represented by the model. Simply take the regression variation and divide it by the total variation. That quantity is called R squared. So R squared for our diamond example is the percentage of the variation in diamond price that is explained by the regression relationship with mass. Some facts about R squared that you need to keep in mind. Just to remind you, R squared is the percentage of the variation in the response explained by the linear relationship with the predictor. R squared has to be between 0 and 1 because the regression variability and the error variability, the sums of squares, add up to the total sums of squares, and they're all positive, so that forces R squared to be between 0 and 1. If we define R as the sample correlation between the predictor and the outcome, then R squared is literally that sample correlation R squared. R squared can be a misleading summary of model fit. For example, if you have somewhat noisy data and delete a lot of the points in the middle, you can get a much higher R squared. Or if you just add arbitrary regression variables into a linear model fit, you increase R squared and you decrease mean squared error, or the average squared residual variation. So these things have to be taken into mind if you're using them to assess model fit. Anscombe created a particularly stark example of a bunch of data sets with equivalent R squared, equivalent mean and variance in the x's and the y's, and identical regression relationships. But when you look at the scatter plots, you can see that the fit has very different meanings in each of the cases. So let's look at the outcome from that example Anscombe and see what it shows. And here it is, the 4 data sets. The first one is a nice regression line, exactly sort of along the lines of what we think of when we think of as just a slightly noisy x-y relationship. The second one, clearly there's a missing term in order to address some of this curvature in the data. The third one, there's an outlier. And in the fourth one, all the data is stacked up at one particular location, and then there's one point way out at the end. So you can imagine getting this if you had the first example and you deleted a lot of the points in the middle. So in all these cases you have an equivalent R squared, but this summary to this single number certainly has thrown out a lot of the important information that you get from a simple scatter plot.